Hey everyone, and welcome to The Explainer. I am so thrilled you're here, because today we are taking a seriously fascinating journey. We're going to zoom all the way out to look at water on a massive global scale, and then we're going to shrink right down to examine the microscopic chemistry of just a single drop. It's honestly an incredible story about what water actually picks up along its path before it ever even reaches your tap. Let's get right into it.
So here is a number to hook you right away, 75%. That's the estimated amount of the Earth's surface covered by water. It is literally nature's most abundant and useful compound. But here's the thing. While water is absolutely everywhere, it is almost never just pure H2O. What's actually hiding inside that 75% is the stuff that truly impacts our daily lives, our homes, and our industries.
Here's our roadmap for the explainer today. First, origins of our water. Second, unseen impurities in water. Third, the hard water truth. And fourth, making sense of measurements.
All right, let's dive into Section 1, Origins of our Water.
Surface water actually presents a really fascinating spectrum of purity. If you look at rainwater at the top there, well, it's technically the purest natural form because it comes from evaporation. But even as it falls through the atmosphere, it starts acting like a magnet, dissolving gases like CO2 and sulfur dioxide. Then you have river water. That has a ton of contact with the soil, so it picks up dissolved minerals and organic matter from decomposing plants. Lake water tends to have a more constant composition, kind of high in organic matter, but lower in dissolved minerals. And finally, at the bottom, seawater. This is the most impure natural form out there, carrying a massive 3.5% load of dissolved salts, mostly sodium chloride.
But what about the water under the earth? Think of this through what I like to call the hitchhiker analogy. As rainwater percolates deep down into the earth, it acts like a giant sponge. The soil filters out suspended particles, making the water look crystal clear. But actually scratch that. Visually clear definitely does not mean pure. As it travels down to the hard rock, it picks up invisible passengers. We're talking high amounts of dissolved mineral salts. Because of this whole journey, underground water usually has great organic purity, but man, it carries a very heavy chemical load.
Moving right along to Section 2, Unseen Impurities in Water.
Natural water is usually contaminated by three distinct classes of impurities. First up, physical impurities. These are the things that affect the color, taste, and odor, like iron salts giving a yellowish-red tinge. Next, we have chemical impurities. This includes acidity, dissolved gases like ammonia, and, this is absolutely crucial, mineral matter like calcium and magnesium ions. Finally, biological impurities. Think algae, fungi, and pathogenic bacteria. Now, surface water often struggles with those biological impurities, but deep underground well water, that's usually biologically pure, even if it is chemically heavy.
The really important point here is that these impurities aren't just a matter of the water being, gross. As this quote from our source material explains, biological impurities actively damage infrastructure. Algae, fungi, and bacteria form slime. And that slime clogs spray nozzles, it ruins circulating pumps, and causes some serious fouling and corrosion in industrial equipment. These impurities are a totally active, destructive force.
Which brings us to Section 3, the hard water truth.
Now, this chemical reaction brilliantly illustrates what hardness actually is. You know how hard water simply refuses to lather up when you add soap? Well, why is that? Because when sodium stearate, which is your soap, reacts with the calcium ions in the water, it doesn't make bubbles. Instead, it forms an insoluble precipitate. It literally binds with the soap to form a solid scum. That is exactly why your clothes might look dingy, your glassware gets spotted, and your hair feels kind of dull when you wash it in hard water.
But hey, not all hardness is created equal. Total hardness is actually the sum of two different types. First is temporary, or carbonate hardness. This is caused by dissolved bicarbonate salts of calcium and magnesium. It's called temporary because you can literally just boil the water to remove it. On the flip side, we have permanent, or non-carbonate hardness. That's caused by dissolved chlorides, sulfates, and nitrates of calcium and magnesium. Boiling won't do a single thing to these. You absolutely have to use chemical treatments, like ion exchange water softeners, to get rid of them.
So what happens when you heat up temporary hard water in a boiler or your home's hot water heater? A super frustrating household nuisance. The heat decomposes the calcium bicarbonate, yielding water, carbon dioxide gas, and importantly, solid calcium carbonate. That solid drops out of the water and forms a crust. We call this scale. It deposits right onto the metal heating elements of your appliances, basically insulating them. This slows down the heating process, forces your appliances to work way harder, and totally drives up your energy costs. But here is a fun fact I found super fascinating. If you boil hard water in a kettle that has a plastic polypropylene lining, that calcium carbonate scale won't actually stick to the sides. The chemical properties prevent it from adhering to the plastic. So instead, the crusty scale just floats right on the surface of your water. Obviously not very appetizing for your morning tea, but pretty great for keeping your kettle clean.
Okay, final stop. Section 4, Making Sense of Measurements. Listen, we gotta bust a massive myth right here. People very often confuse hardness with TDS, which stands for total dissolved solids. They are absolutely not the same thing. Hardness measures only the concentration of specific minerals, primarily those calcium and magnesium ions. That's it. TDS, on the other hand, measures all the dissolved solids in the water. So if your water report says you have 300 ppm TDS and 10 grains hardness, they are definitely not describing the same property of your water. To help us understand the units better, hardness is universally converted and expressed in terms of calcium carbonate equivalents. It just gives us a standard baseline. The most common unit you're going to see is parts per million, or ppm. 1 ppm is exactly equal to 1 milligram per liter. Then you have some older or more regional units. A degree French is 10 milligrams per liter, and a degree Clark, used mostly in English metrics, is about 14.3 milligrams per liter.
And then there's this magic number, 17.1. In household discussions, especially if you're out shopping for a water softener, hardness is often reported in grains per gallon. 1 single grain per gallon equals exactly 17.1 milligrams per liter of calcium carbonate hardness. So if someone tells you your water has 10 grains of hardness, you just multiply by 17.1, and boom, you realize you've got about 171 milligrams per liter of hardness floating around in there.
So how do chemists actually figure these numbers out in a lab? Well, they use the EDTA method. It is a really clever test. At a very specific pH of 10, which is maintained by an ammonia buffer, EDTA forms a colorless, stable complex with the calcium and magnesium. By using a special indicator that changes from wine red to blue as the reaction completes, chemists can perfectly estimate exactly how much hardness is hiding in that water sample.
Which brings us to the end of our journey today and leaves us with a pretty provocative question to consider. The calcium and magnesium in hard water aren't actually necessary to remove for health reasons. Your water is perfectly safe to drink. But, as we've seen from its long journey through the soil and into your home, is its invisible hardness slowly scaling your pipes, ruining your water heater, and driving up those energy bills? Understanding the chemistry really is the first step to protecting your home. I hope this explainer gave you a crystal clear look into the water we take for granted every single day. Thanks so much for joining me. Keep learning, and I'll see you in the next one.